You know those incredible satellite images you see all over the place? Ever stop and wonder how they're actually made? It's way more than just pointing a giant camera at Earth. See, behind every single pixel is a whole series of critical, super calculated decisions about that satellite's orbit. So let's dive into how those choices literally shape how we see our world from space.
So let's say it's your job. You're designing a brand new mission to observe the planet. What's the single most important choice you've got to make? Well, it all comes down to the satellite's orbit. That one decision pretty much determines everything else. When we see a place, what time of day we see it, and from what exact angle.
And the very first choice you have to make is also the most basic one: altitude. Do you want your satellite flying kind of close to the Earth or way, way out there in deep space? This one decision sets up the biggest, most fundamental trade-off in all of Earth observation.
On one hand, you've got low Earth orbit, or LEO. This is where most of the imaging satellites live, flying relatively close so they can get those incredibly detailed shots. But what's the catch? Well, they're moving super fast, so it might take days or even weeks to pass over the exact same spot again. Then, on the other hand, way out there, you have geostationary orbit, or GEO. Satellites here are basically parked over one spot on the Earth. This is perfect for constant monitoring, like tracking a hurricane in real time. The trade-off is, from that far away, the detail you can see is much, much lower.
And just how big is that difference we're talking about? Well, a GEO satellite is chilling about 36,000 kilometers away. A LEO satellite might be at, say, 700. That's not just a little bit higher, it is 50 times farther out. And you got to remember, when it comes to satellite imaging, distance is the absolute enemy of detail.
Okay, so most high-detail satellites are in low Earth orbit. But that brings up a whole new problem. If you take a picture of a field on a Monday morning and then another one on Wednesday afternoon, the lighting's going to be totally different, right? That makes any kind of scientific comparison basically impossible. So mission designers came up with this really, really clever solution.
It's called a Sun Synchronous Orbit, or SSO for short, and it is the absolute gold standard for imaging. The satellite's orbit is angled just right so that it kind of shifts or precesses just enough each day to perfectly follow the sun. So what does that get you? It means the satellite always crosses the equator at the exact same local time every single time it passes over. This makes sure the lighting conditions are consistent day after day, year after year.
Right. So these satellites cross the equator at the same local time on every single pass. And for a ton of missions, that magic moment is 10:30 a.m. Why so specific? Why not noon or 9 a.m.? It is definitely not random.
Turns out, 10:30 in the morning is this perfect strategic sweet spot. The sun is high enough in the sky to give you great illumination, but without casting those long, distorting shadows you get early in the morning. But maybe even more critically, it's early enough to avoid all the cloud cover that tends to build up in the afternoon in a lot of places. It's the perfect balance for clear, consistent science.
Okay, so we've picked our altitude, we've got our time of day dialed in, but how do we make sure we eventually see the entire planet? This brings up another classic trade-off: the width of the satellite's view versus how long you have to wait to see the same spot again.
Honestly, the best way to picture this is to think about winding a ball of yarn. As the satellite is orbiting, the Earth is constantly rotating underneath it. So each pass it makes lays down a new thread on the globe. And over many days, all those threads build up until you have a complete picture of the entire planet.
And this is where something called swath width comes into play, which is just how much ground the satellite can see in a single pass. If you have a really wide swath, you can cover that whole ball of yarn much faster, which gives you a quick repeat cycle. But if you want super high-resolution images, you need a narrower swath, which means it takes a lot more passes and more days to cover the whole globe. The famous Landsat program, for example, it has a repeat cycle of 16 days to image the entire Earth.
But what if you can't wait 16 days? What if something really important happens just off to the side of the satellite's path? Well, this is where the satellite's own agility becomes so important. It's not just about the orbit, it's about how the satellite chooses to look down at us.
So, a satellite can look straight down. That's called a nadir view. This gives you the cleanest, most geometrically perfect picture you can get. The problem is, it's restrictive. You can only see what you fly directly over. The alternative is off-nadir viewing. This is where the satellite physically tilts its camera to look off to the side. This gives it incredible flexibility to see things that aren't on its direct path, but it can introduce some distortions, making tall buildings or mountains look like they're leaning over.
And this is exactly why that agility is so important. Off-nadir viewing isn't just some technical feature, it's a game changer.
It means we can point a satellite at a wildfire or a flood zone today, when that information is absolutely critical, instead of having to wait, 5 or 6 days for the orbit to just happen to line up perfectly.
All right, so we've got the right orbit, we've got the right viewing angle. Now for the final piece of the puzzle, the camera technology itself. How does the satellite actually build the image of the ground down below?
There are basically two main methods. The older style is a frame camera, which works just like the one on your phone. It takes an entire rectangular snapshot all at once. But the modern standard is the push-broom scanner. You can imagine it as this long line of sensors that gets pushed forward by the satellite's motion, building the image line by line, kind of like a flatbed scanner. It's way more efficient and produces incredibly high-quality data.
So what does this all add up to? Every single choice we've just talked about, the altitude, the orbit, the viewing angle, the sensor, it all works together toward one goal, producing what's called analysis-ready data. This is data that's already been corrected for things like atmospheric effects, so scientists can just get to work and focus on what really matters, understanding our changing planet.
So the next time you see a satellite image, remember the story it tells. It's a story that's jam-packed with trade-offs: detail versus frequency, consistency versus flexibility. It's a great reminder that every single view of our planet from space is a result of 1,000 careful decisions, all designed to give us that perfect glimpse of the world below. What choices were made to show you the world today?